Welcome to our machine learning presentation, led by Dr. Microlearning in January 2026. Over the next few minutes, we'll walk through core ideas, methods, challenges, and real-world use cases, aiming to give you a clear, practical overview whether you're new to the topic or refreshing fundamentals before diving deeper. This slide outlines the journey ahead, listing 6 main sections from an introduction to practical applications and challenges. Think of it as our roadmap. We'll start with basic definitions, move through learning types and algorithms, explore evaluation and pre-processing, and finish with concrete applications you can relate to. Let's begin the first part, an introduction to machine learning, where we'll set the stage with definitions, historical context, and why these methods matter today, so you have a solid foundation before we unpack specific techniques and examples. Machine learning is a branch of AI that lets computers learn from data and make decisions without explicit instructions. It includes supervised, unsupervised, and reinforcement approaches, and uses algorithms to detect patterns, predict outcomes, and improve performance over time, as shown in the visual summary on this slide. This timeline highlights how machine learning evolved. Early roots in statistical models and foundational computing ideas led to neural network breakthroughs in the 1980s, with deep learning's rise in the 2000s, and modern advances driven by big data, cloud computing, and greater computational power, enabling today's sophisticated systems. Machine learning powers 4 major value areas: automated data analysis that extracts insights from massive datasets, personalized recommendations that tailor user experiences, predictive modeling for forecasting and diagnostics, and autonomous operation that underpins self-driving cars and robotics, each illustrated in the boxes on this slide. Now we move into types of machine learning so you can see how different methods fit different problems, from labeled data approaches to models that learn by exploring environments, and why choosing the right type matters for accuracy and practical deployment. Supervised learning trains models on labeled input-output pairs so they can predict or classify new examples. Models learn by comparing predictions to actual outcomes and correcting errors over time. This approach is widely used in spam detection, image recognition, and structured language tasks where reliable labels exist. Unsupervised learning finds hidden structure in unlabeled data, helping discover patterns and groupings without predefined targets. Common techniques include clustering for customer segmentation and dimensionality reduction to simplify complex datasets, while keeping essential information for visualization and pre-processing. Reinforcement learning focuses on an agent interacting with an environment, learning policies that maximize cumulative rewards. It's ideal for sequential decision problems and has powered breakthroughs in robotics, game playing like AlphaGo, and autonomous systems where trial and error learning helps optimize long-term outcomes. Next, we'll cover foundational concepts you'll rely on throughout the course, including how data is represented, split, and evaluated, so you'll understand the building blocks behind model training and why they matter for reliable performance. Features are the input variables a model uses to describe patterns, while labels are the target outputs the model aims to predict. Together, they form the basis of supervised learning, with models learning to map feature patterns to correct labels during training. Training and testing splits separate data into a subset used to teach the model, and a separate set to evaluate its generalization on unseen cases. Maintaining a representative, balanced split is crucial to reduce bias and get a realistic sense of model performance. Common evaluation metrics give different views of model performance. Accuracy shows overall correctness, precision and recall, balance, false positives and missed positives. The F1 score harmonizes precision and recall for imbalanced datasets, and ROCALC captures classification trade-offs across thresholds. Now we'll explore common algorithms, starting from simple linear models to complex neural networks, highlighting where each shines and what trade-offs to expect when applying them to real problems. Linear regression models predict outcomes by assuming a linear relationship between features and the target, making them straightforward to implement and interpret. Because of their simplicity, they're often a first step for forecasting, trend analysis, and resource allocation in finance and marketing contexts. Decision trees use a tree-like structure of decisions and outcomes, which makes them intuitive and easy to visualize. They handle both classification and regression, but can overfit without pruning, so regularization and careful tuning are important when using them for segmentation, fraud detection, or medical diagnosis. Neural networks are inspired by the brain and consist of layered units that transform data. They excel at unstructured data like images, audio, and text, and deliver high accuracy with enough data and compute, powering breakthroughs in image recognition, natural language processing, and autonomous systems. With the methods explained, we'll next consider common challenges in machine learning, including model complexity, data quality, and the trade-offs that dictate performance, so you can anticipate pitfalls and design better experiments. Overfitting happens when models capture noise instead of true patterns, hurting generalization, while underfitting occurs when models are too simple to learn essential relationships. Techniques like L1 and L2 regularization help constrain complexity and improve performance on unseen data. Data preprocessing is essential, handling missing values through imputation, removing noise to avoid distorted learning, and applying feature scaling like normalization or standardization all help models converge faster and make more reliable predictions by aligning feature ranges. The bias-variance trade-off explains model behavior. High bias oversimplifies and misses patterns. High variance reacts too strongly to small data changes. And finding the right balance often requires model selection, hyperparameter tuning, and cross-validation to optimize real-world performance. Now we'll shift into applications, showing where these techniques make tangible impact across language, vision, and personalized systems, and how you might leverage them in your own projects or products. In natural language processing, machine learning enables text classification, sentiment analysis, translation, and conversational agents or chatbots. Speech recognition converts audio to text, and large language models support predictive text generation and content automation, improving communication and user interactions. Computer vision models identify and classify objects in images, assist medical imaging by analyzing scans, enable real-time video processing for surveillance or augmented reality, and power aesthetic tools that optimize photo editing and content creation for professional and personal use. Recommender systems personalize experiences by suggesting products or content based on user behavior, increasing engagement and revenue, supporting better decision-making through data-driven predictions, and ultimately enhancing user satisfaction with tailored recommendations. Thanks for watching this overview of machine learning. I hope you found the explanations clear and practical. If you'd like to dive deeper into any section, explore a hands-on tutorial, or discuss real-world applications for your project, let me know and we'll continue from there.